Hi there guys, so we're going to go through question 1a from exercise 12J in the book, and the reason why I'm doing this is because in the example which comes beforehand they talk about using Euler's method, and in fact in the first question for these second order differential equations they actually don't want you to use the technique which they've shown you in the example question, which is kind of frustrating because the example which comes before is the first example that's turned up for several exercises now, and we're not actually using that to start off with at least. Okay, so anyway, let's have a look at this one. So it says, by writing each as a coupled first order differential equation, solve the following equations to find x in terms of t. Okay, so we're given the second derivative, minus 3 lots of dx dt plus 2x is equal to 0, and we're given some initial conditions as well. So we are not doing this via Euler's method. So how are we going to do it? Well, let's start off by saying that we can let the dx dt equal to y. So we can rewrite this thing as dy dt. So this would be the second derivative of this thing here. So in other words, just differentiate this thing here again, and we'll get the second derivative. And if, of course, we call dx dt y, then this thing is dy dt. And we're getting minus 3 lots of y plus 2x is equal to 0. Equal to 0 there. And, of course, that gives us dy dt is equal to minus 2x plus 3y. I'm going to put it in terms of x and then y because that's just going to help me out a little bit with my matrix. And then we're going to write down, of course, the other one, the substitution that we've used. So dx dt is simply equal to no lots of x plus y. So that one's just going to be equal to y there. So we can write this down now in terms of matrices. We can say, well, x dot y dot gives us the matrix 0, 1, and minus 2, 3. It's meant to be a 3 there, so 3, and that's as applied to x, y. And now we need to solve this, and so we're going to solve it using eigenvalues and eigenvectors. So we need to set the determinant equal to 0 when we're subtracting lambda from the diagonal of our original matrix, which we've done lots of times before, of course, but just to do it again, we're just going to do the technique here. So we're going to do 0 minus lambda there, 1 and minus 2 and 3 minus lambda there is equal to 0. Now, maybe I'll skip through a few of the steps here. If you multiply this out, so obviously if you do this times this, take away this times this, and set it equal to 0, you can expand those, and then you can simplify it. And when you simplify it, factorize again, you're going to get x minus 1 and, lambda minus 1 and lambda minus 2 is equal to 0. So lambda 1 there is equal to 1, and lambda 2 is equal to 2. Just to recap what we did there, we said this times this, take away this times this, is equal to 0. That's how we set the determinant equal to 0. I've skipped out the working out, which is then to multiply out the brackets, to simplify, and to factorize again. And when we factorize again, we get this, and that gives us our two eigenvalues. Lambda 1 is equal to 1, and lambda 2 is equal to 2. Now, eigenvectors, again, you should have had lots of practice at this by this stage. We would just need to substitute this into here. Okay, so we can put in, for example, when lambda 1 is equal to 1, we can put that in, so we're getting minus 1, 1, and minus 2 there. And again, if we substitute in 1 into here, we're also getting out minus 2. And that's applying to xy here to give us 0, 0. Okay, now again, that's the technique that we've done a lot of times before. And so if you're confused on that, you need to look at previous videos. But now we just need to times this by this to get this. Or likewise, it will give you the same equation if you times these by these, sum them together, and you get the answer here. So there's a kind of a check here to see that we're getting the right equation. So we're getting out minus x plus y is equal to 0, or likewise minus 2x plus 2y equals to 0. I can see I've made a mistake there. That should have been 3 minus 1 should give me plus 2 there, so that's a plus 2. Okay, so then I'm getting y is equal to x, and that's giving us the eigenvector of 1, 1, or 2, 2, or 0.5, 0.5, but obviously 1, 1 is the easiest choice to make there. Now, if you do exactly the same thing with lambda 2, you end up getting the second eigenvector, and the second eigenvector gives you 1, 2. You can do that. You just need to put this into here again in the same format like this, and then create your equation. You end up getting y is equal to 2x for this one, and this is your second eigenvector. Okay, so I'm going to get rid of everything on the page here. Obviously, you can go back in the video if you need it. I'm going to get rid of everything here. We've done now what we needed to do to find the eigenvalues and the eigenvectors. So we've got 1 and 2 and 1, 1 and 1, 2. So now we can use the standard format for our solutions to these equations, which is that xy is equal to a e to the lambda 1t, so that lambda 1 is 1, so that's just t. We put in our first eigenvector that's associated with lambda 1, that's just 1, 1, and plus b, lots of e to the power of the second eigenvalue, which is 2, t there, and then the eigenvector associated with 2 was 1, 2. Okay, so there's our general set of solutions. Now, it is worth noting that y is actually dx dt, or in other words, x dot there. Okay, so it's not actually y. Y is the thing which we created earlier on. Okay, so in fact, all we really care to find is the x formula, because that's what it's asking us to do, x in terms of t. So the x formula is going to be this top part here and this top part. So we will not be interested in these bottom parts at all. Now, we need to work out what a and b is with the conditions here. So with the conditions, we've got x is equal to 2 and y is equal to 4. Y, of course, remember, is the same as dx dt. And we can set that equal to a. Now, e to the 0, when we put t as 0 in, is going to give us 1. So that gives us out 1, 1 there, plus b. And then again, e to the 2 lots of 0 is still going to be 1. So we'll get b lots of 1, 2. So we're going to get two simultaneous equations. We get 2 equals a plus b. And we're also going to get 4 equals a plus 2b. Now, it turns out that the solutions to those are b is equal to 2 and a is equal to 0. So we're getting b equals to 2 and a is equal to 0 there. So that means that a is equal to 0. So in fact, the whole of this is going to disappear. And b is equal to 2, so we'll get the 2 in front of this. So ultimately, in terms of the top line, we'll just be left with 2e to the 2t times by 1, which is 2e to the 2t. So finally, we could restate this with a and b written in it, but basically, let's put it like this, x and then x dot is equal to, this disappears, and we'll get 2 lots of e to the 2t and 1, 2 there. And then, of course, if we're just interested in x, that's just going to be the 1 times by this. Of course, if we were just interested in x dot, it's the 2 times by this. So we're getting x is equal to e to the 2t. Sorry, 2e to the 2t. There we go. That's the final answer in this case. So we're not interested in the second solution of dx dt because they're not asking for that in this question. Okay, right. Let's just have a look at what it says in the book. So let's go to the answers on this one. And there we go. We can see we've got x is equal to 2, e to the 2t there. Okay, so in other words, with this exercise here, what's important to know is that they might be asking you to use Euler's method, or they might be asking you to use the exact method rather than finding approximate solutions. So the exact method, of course, let's just go back and show you this. Where was it? 2f. So we're getting solutions which are looking like this, basically. I think 2f might have been the first time when we saw that. Okay, so that, yeah, exact solutions of coupled differential equations. So again, that came from the explanation from this investigation, in fact, and we ended up with this box here, which is obviously the thing which we're using many times over. So that's what we've just used. So in the exercise, sometimes you'll be using this method, and sometimes you'll be using Euler's approximate method. Okay, guys, thank you for listening in, and good luck with the rest of the exercise.